My slide is visible?
Yes, sir.
Yes, sir.
Okay. So today is going to be the first theory class on refrigeration and air conditioning systems. So we'll begin with the classification of refrigeration cycles. So just like all the power cycles are classified into two categories, one is gas cycle and the other one is vapor cycle. So does the refrigeration cycle. Okay, so thermodynamics does not differentiate between a refrigeration cycle or a power cycle. So what is the difference between a power and a refrigeration cycle in terms of the directionality of the processes? So it could be any property A and B on which you are plotting the cycle. So in which direction the power cycle moves and in which direction the refrigeration cycle moves? Any idea? So you can have a cycle going in the anti-clockwise direction. You can have a cycle going in the clockwise direction. So which one leads to a power cycle and which one leads to a refrigeration cycle? Can anyone
The
answer this?
power cycle can be anything clockwise cycle and
So there are only two options: clockwise cycle for power cycle or anti-clockwise cycle for power cycle. So which one is for power cycle?
clockwise
Clockwise is for power cycle.
power cycle.
So this one is for the power cycle. So you can have TS or you can have pH, different properties you can use to plot the cycle itself. But as long as the cycle moves in this direction, you will see it's a power cycle. And the refrigeration cycles are moving in the anti-clockwise direction. So if you join all the points in the cycle and give the arrows, you will see that refrigeration cycles are always moving in the anti-clockwise direction. Okay, so uh, that's all that differs. No? So as far as the cycle per se goes, there's no difference in the processes itself. It's just that heating process becomes cooling process becomes heating process. Okay, compression becomes expansion, expansion becomes compression. So such differences will happen between power and refrigeration cycle. So that's why when we do the classification, we need not classify as power and refrigeration cycle. It's better to classify them as a gas cycle and a vapor cycle. Okay, and for every cycle which you have in the gas cycle, you can have the reverse one doing the opposite work. So if one is power cycle, the other one becomes the refrigeration cycle. So many a times the textbooks, they just simply mention about power cycles and they do not mention about the refrigeration cycle because it is quite obvious. So as the name suggests, the classification is based on the working fluid. Working fluid. Okay. The fluid or solid or fuel from where you are deriving energy, it can be solid, liquid, gas. We do not classify the cycles based on what is the external media. Okay, so your power cycle could be getting energy by combusting petrol, diesel, by burning coal. Okay, the cycles are not on the basis of the fuels per se, but the classification is based on the working fluid. So the fluid which is actually flowing through the internal components of the device. Okay, so if the fluid, the working fluid is only in the gaseous phase and does not change its phase during the entire course of the cycle, then it is classified as gas cycle. In case it changes its phase from gas to liquid and then liquid to gas, then it is classified as vapor cycle. Now, so if you plot again the two-phase region, so if you have a cycle which operates in this region, it would be classified as a vapor cycle, if you have a cycle which operates in this region of the working fluid. So this TS diagram is for the working fluid. It could be water, it could be air, it could be a refrigerant, it could be helium, hydrogen, any gas or any fluid that you can think of. So if you are working in this region where you can have phase change, then the cycle is vapor cycle. If you're working far away from this dome, the entire cycle is somewhere here, then it is classified as gas cycle. Some examples are given over here. So since we are reading about refrigeration, so this reverse word would be very common. So reverse Brayton is the refrigeration cycle used in airplane air conditioning, where air is used as the refrigerant, or in this case, a more general term would be the working fluid. Okay, Stirling refrigerators are also there, which I had discussed in the introduction class. So it is used for very niche applications, for cryo-cooling applications, to preserve the temperature within the vessels which are carrying liquid fuels. Okay, the other one is the vapor cycle. The most common one is the cycle which we are using in our day-to-day life, which is commonly known as vapor compression refrigeration cycle. But in principle, it is the reverse of the Rankine cycle. So if you look at the Rankine cycle, reverse it, it becomes the vapor compression refrigeration cycle with one small modification to one of the devices in the Rankine cycle. Okay, then there are other cycles also which fall under this vapor cycle category, but you wouldn't have studied in your thermodynamics. So one of them is the vapor absorption. Okay, you can have absorption, adsorption. So basically, this is that cycle which I was describing in the previous class, where you use certain material which has affinity to the working fluid. So if your working fluid is water, you can have some salts which have affinity to water vapor, and they can actually be used for producing refrigeration, and they would be driven not by a compressor. The motion is driven by thermal energy. So you provide heating, cooling in certain chambers, and you can reverse the directionality of the flow of the working fluid. So people started off with the sulfuric acid and water, and then they moved to water ammonia cycles and water lithium bromide salt cycles. So few cycles are right now available, and there are commercial products based on them. Okay, there are other ways of compressing the working fluid, and one of them is using a secondary high-speed jet. So these are again not the common cycles which we discussed in the second year thermodynamics. So this is something called as a vapor jet, where you use a primary jet to entrain a secondary jet. So you can have a primary high speed flow, and then you can have an inlet port from where you entrain the secondary working fluid, which is your refrigerant. And then you can use this ejector to compress the secondary fluid. So these are different ways of performing the compression of the vapor compression. Okay, so they again are not very common. So these systems are again used where you have a primary jet available. So mainly in power plants where we have some bleed gas available and we want to produce some refrigeration with that available high speed steam. So then we may go for vapor jet, or industries where a lot of heat is available, let's say at 70 to 80 degrees C, which we would have rejected to the ambient. Now we can use them for producing some amount of, let's say, chilled water, or you want to preserve something. So in case that particular industry also has some chilling requirement or chilled water requirement, they can use that 80-degree heat which they were going to reject to the ambient to produce some amount of refrigeration and reduce their power bills. Okay, so such systems are not very common, but they have their own area of application. So in the initial phase, we will focus mainly on the vapor cycle being the vapor compression refrigeration system, the cycles which operate uh, using this cycle. And then we will discuss about the reverse Brayton and the reverse Stirling cycle. So as is all the customary practice, we always start with the Carnot cycle because we have been introduced to Carnot cycle right from our school days and then again in our uh, initial UG classes. So we all know that this is the benchmark cycle and hence any textbook, any uh, uh, any study material on thermodynamic cycles will always start with this as the reference cycle, and then we move on to certain practical issues with the Carnot cycle, and then we discuss about the actual cycle. But from the introduction class, it should be clear that that's not how things might have happened uh, in the history. Okay, so things were moving simultaneously. So no one had the a priori knowledge of thermodynamics and what is reversible process. No one had everything documented and provided to them in form of an internet material or a textbook. So things were happening simultaneously. So this we know that a TS diagram of Carnot cycle is a simple rectangle. Okay, now you see the directionality given for this refrigeration cycle. So let's look at the components that will be there. So 1 to 2, 1 to 2. What is the process in a Carnot cycle 1 to 2? What is this process? Isentropic what?
Expansion.
1 to 2 is expansion. So always think of the, the pressures over here and pressure over here. So this top line will be at a higher pressure or a lower pressure.
Higher pressure.
So given that the direction of the process is 1 to 2, then what is this process? 1 to 2 isentropic
Compression.
compression. So 1 to 2 is isentropic compression. So we put a compressor over there. Then 2 to 3 is for the timing, forget about this dome. So cooling process. Okay. Isothermal. Okay. So we put some heat exchanger to reject heat. Then 3 to 4 is the expansion process, again isentropic. So we put a turbine in this case, which will expand the gas and produce some work. And then 4 to 1 is isothermal heating process for the working fluid. So we will have to provide another heat exchanger which will absorb heat. So we have these 4 components in place. And then why put the turbine and a compressor on a separate shaft, and this turbine will produce the work, we convert it into electricity by a generator and then feed it to the compressor. So instead of doing all that thing, we can put them on a single shaft and we can mount them on a single shaft. So whatever amount of work is produced by turbine, it would be consumed by the compressor, and some additional work will have to be provided externally. So that can be provided by a motor. So all these three, in fact, can be mounted on a single shaft. So this would be the component. Now, which process is actually difficult to attain? Forget about the liquid vapor dome right now. Whatever you have studied from your second year thermodynamics, which process is actually very difficult to attain, and hence people were looking for other cycles also. So even though Carnot cycle was the most efficient, we didn't stop at this cycle itself. So think of, do not think of the vapor cycle, just think you have air as the working fluid. And you have to get this rectangle working out of it. So which process would have been a very difficult process to attain? So even now also we think of the ideal compressor being isentropic compressor. Okay, the ideal turbine being the isentropic turbine. Okay, so for the time being, assume that that is possible with the best efficiency. We can attain an isentropic efficiency close to 0.9 or 0.95. Let's assume that. So what happens is this isothermal processes. This is where the difficulty arises. Okay, so if you look at the isentropic efficiency of a compressor in your refrigerator, it is around 65%. AC will have somewhere around 65 to 70%. The large compressors that we use in our Nalanda refrigeration system, that is again close to 75%. So that is the maximum that we have been able to attain. But still, we can envisage that we can probably push it to 80%. Okay, so we can attain the isentropic process with 20% inefficiencies. But when it comes to this isothermal heat transfer, that is a challenge, especially with a gas cycle. If you have air as your working fluid, then it becomes very challenging to transfer heat in an isothermal manner. So how do we transfer heat? So let's understand how do we transfer heat in an isothermal manner. So it has to be reversible also. So reversible isothermal manner. So it's not just isothermal. So how do we transfer heat in an isothermal manner? So when we are discussing about gas, okay, then we will discuss about the vapor. So if you have air inside a piston cylinder assembly, what will happen from 2 to 3? Forget about this line for the time being, the liquid vapor line. So I have to transfer heat from air to the surrounding in an isothermal manner. Air is trapped within this piston cylinder assembly. So can anyone tell me how to do that? This is the surrounding. And that too reversible. Let's say the surrounding is at 40 degrees C. So what should be the temperature of air? Let's go step by step. The surrounding is at 40 degrees C. What should be the temperature of air for the entire process 2 to 3 to be reversible isothermal?
40 degrees.
40 degree.
Can you see the first issue? You have to transfer heat from a 40-degree gas to a 40-degree surrounding. Is it possible? There is no potential of heat transfer. That is the first issue. So let's raise the temperature a little bit. Okay, extremely small amount of temperature rise we can provide by compressing this gas. We compress this gas. So let's say the piston moves to this. For the time being, assume that after this much displacement of compressor of the compression process, you have only a very small amount of temperature rise in the gas. Let's say 40.0001 degrees C. It goes to slightly higher temperature. Now you can transfer this heat to the surrounding. Okay, again you let it cool down to 40 and again compress the gas a little bit and again allow it to cool down. So this is how you will be transferring the heat from this process point 2 to 3 in case the working fluid was gas, let's say air here. So basically what is happening is in 2 to 3 you are still compressing the gas as well as you are transferring heat to the surrounding. So this is not an isobaric process. Okay. So again, I am telling you, please do forget about the liquid vapor line. We'll come to the vapor cycle a little bit later. So this is what you would have studied in your +2, that you would have studied in your UG classes also. So you will always assume that the working fluid is trapped within the piston cylinder assembly. This is the isentropic compression, isothermal heat transfer, then isentropic expansion, and then again heat transfer. So in case you have to absorb heat, you will have to do the reverse process. You will have to start expanding the gas so that the gas slightly cools down and then it absorbs the heat, comes in equilibrium with the surrounding. Again, you expand. So this entire process is going to be very, very slow. So this is going to be very, very slow process. Now, what is the issue with slow process? We will see later on that the capacities are poor. You may have a very efficient cycle or a system, but you will have very small capacities because you will realize that the rate at which you are cooling the gas or heating the gas, or suppose you have a compressor which is an isothermal compressor instead of an adiabatic one, you will see that your MCP delta T's divided by the time in which the cycle is operating, this number is almost going to be 0. Whenever you have isothermal processes, this is the biggest issue. So over here you have reversible isothermal. So another issue is you will see you will have to work with almost 0 delta T between the working fluid and the surrounding, which is another issue. We have studied in heat transfer that the potential for heat transfer is the temperature difference, and that temperature difference we are making it to 0 in order to make it reversible. And then the isothermal process itself is very, very slow. So you will have a very efficient system which is producing almost negligible heating or cooling capacities. Okay, so this is as far as the gaseous cycle goes. Now one can say that we know that isobars and isotherms are same when we move on to a vapor cycle when we have phase change. So one intelligent way of uh, trying to devise a reverse Carnot cycle would be to put these isothermal lines inside a dome. Then you can say that isobaric process and isothermal processes are same. So I can have a heat exchanger where, let's say, the pressure drop because of the friction within the tubes are negligible. So why we can assume this process to be isobaric from 2 to 3 in case of a heat exchanger. Let's say you have any heat exchanger. Okay. So why we assume P3 equals to P2 is we are neglecting the viscosity of the working fluid itself. So we forget about the viscosity. We forget about our friction factors that we have studied in fluid mechanics. We forget about F equals to 64 by RE or the Moody's diagram that we have studied, that for any pipe flow, the fluid will have pressure drop because of the property viscosity. So we neglect that, and hence we assume that the pressure of the fluid at the inlet and at the outlet of this heat exchanging tube would be same, which is of course not the case in practical scenario. But we move ahead with this assumption, and that's why we draw an isobaric line in case of heat exchanging processes. And now if this isobar is placed inside a dome, liquid plus vapor region, it becomes an isothermal. Very clever way of having an isothermal process. Okay, and I don't need to have the compression and expansion process within this, because simple isobaric heat transfer process will also lead to an isothermal process. So I get rid of that additional expansion and compression that I had to do for the air. So that's the advantage of putting these 2 to 3 and 4 to 1 inside your liquid vapor region. Okay, but then there are no free lunches in thermodynamics. So what now happens is your isotopes are also within the liquid plus vapor region. Now, what is the issue with these two processes? So now you have addressed one issue. So one issue was, in case of a gaseous cycle, it is quite difficult to attain that isothermal heat transfer process, because you have to do a very slow compression and expansion of the vapor of the gas, and it would have led to very small capacities, extremely slow process. Now you have moved on to the vapor cycle and you have put those isotherms inside the dome. You have addressed one issue. Now the issue comes in the isentropic compression within the liquid plus vapor region. What is the issue here?
So the entropy of liquid and vapor differs vastly.
Okay. So what
So
is the issue?
uh, so the from like process 3 to 4, isentropic expansion or 1 to 2 isentropic compression. Like we are changing liquid liquid plus vapor to like pure vapor. So the part with the liquid is converting to vapor, so the entropy difference is high, and we are telling it to be isentropic.
Okay, so you are thinking only purely in terms of thermodynamics. Uh, there are issues, there are practical issues with the compressor or the turbine working in the two-phase region. Was that taught to you or told to you in the thermodynamics class? Just think of the reciprocating compressor. So let's say the compressor is made for only gaseous phase. Okay, gaseous phase. So what is an important feature of gas is it is compressible. Liquid is significantly less compressible. So when we have to compress a gas, what the manufacturers do is they provide very little clearance volume. So when the piston is at the top dead center, the clearance volume within this cylinder is very, very small. And that is how you can attain very high pressure ratios. Now, this is assuming that you have a fluid which is compressible. Now, think that you have a large amount of water present in this, and still your reciprocating compressor will now try to compress it by this much. Okay, it will try to compress that volume of water present in the piston cylinder assembly to this volume. What will happen? There would be a significant surge in the pressure. Okay, so incompressible fluids, if you have even the slightest amount of change in its volume, it will lead to a significant rise in pressure. So there would be an enormous increase in the pressure, and this liquid water will either break away those intake and discharge valves, or it will come out of the sealings between the piston and the cylinder. So liquid will try to come out of here, it will break away these valves and come out of these valves itself. So there would be a catastrophic failure in case you fill liquid for a device where the device was designed for vapor or gas. Okay, so but that doesn't mean that you do not have a hand pump. It is just that the hand pumps will operate with much larger clearance volume. So you will not give such large compression ratios in case of a liquid pumping device. So you have pumps, reciprocating pumps for liquid. It is just that they are designed with larger clearance volumes. They will not have such large change in volumes. So probably the piston will displace from this point to only this point. And within this small change in volume, the pressure would be so large that the discharge valve will open and it will pump the water to the higher pressure. Whereas a gaseous compressor is made to work with very small clearance volumes. Now you have a system where you have to handle both liquid and vapor. Now here comes the issue. I probably, if I design it for this operating condition, what will happen if the operating condition goes to this point? There could be changes in the operating conditions. What if the operating condition goes to this point? So the liquid plus vapor, the quality of the vapor itself in the mixture can continuously change. So I cannot design it for just one particular design condition and think, yes, I will always operate at that point. So there is a design challenge. And then people have actually tried to operate in the liquid plus vapor region. I will show you some photographs of a turbine which operates in that region. So this is can you see the rupture to the blades? Can you see the rupture to the blades over here? Is this visible?
Yes, sir.
So this is what happens when you have a steam turbine having liquid water impinging on the blades. So this is erosion of the blades by pitting. So those liquid droplets, they strike the blades at extremely high velocity and they're eroding it away. So this is what happens when you work in the two-phase region. And hence, even though by this clever placement of the isobar within the liquid plus vapor region, now we are stuck with these two processes. Okay, so the reverse Carnot cycle hence is next to impossible to achieve in a practical scenario. So what is the next bet that we can make is, okay, let's push this outside this region. Okay, something similar could be done over this also. So let's first look at the right hand side. We still maintain that rectangular shape. We just push this isentropic compression which was happening inside the dome, we'll push it to the outside part. And hence comes the first important aspect of the vapor compression refrigeration cycle is the inlet to the compressor should be at least in the saturated vapor region. It should not be in the two-phase region. Then you will have liquid entry into the compressor. Your compressors can fail. So that liquid impinging on the blades that you have seen, something similar can also happen in the piston and the cylinder walls also. So that is one thing. The second thing is, I have already told you, when you try to compress the liquid and you do not have the requisite clearance volume, then you can have catastrophic failures of all the sealings that are there. So hence you would want to maintain the entry to the compressor in the saturated vapor region. It can be superheated vapor, no issues from the compressor life point of view. Okay, so now from here we start compressing. Okay, and we reach to a certain intermediate pressure, and then from here we have to move in an isothermal fashion. So as I told you, part of it is now in the gas region, and now we are faced with the same issue which we avoided by placing the isothermal inside the dome. Now this is no more an isobar. The isobar would have been somewhat this or this. So hence from 2 prime to 2, again it is a compression process in which the compression, instead of being an isentropic compression, has become an isothermal compression. That is exactly what I was telling you for the air example. So now this process becomes very, very slow. First of all, we do not have a compressor which works in an isothermal manner, because all the compressors will have some finite speed. And when you look at those finite speeds, you will see that when you compress a gas at a finite rate, it will not go to 40.0001 degrees and it will wait for you to cool, and then again you will move. So at a finite speed, you will see that the gas is continuously getting heated as you compress. And you cannot have the reversible isothermal process. There will be a delta T. Okay, that delta T will lead to cooling of the gas inside this compressor, but you are no more in this reversible isothermal line. Okay, so this is what is shown in the schematic. So 1 to 2 prime is your isentropic compressor, but 2 prime to 2 is the isothermal compressor, which is the extremely slow compressor. So one compressor is very fast, the other compressor is extremely slow. You will not be able to match the mass flow rates also. So then we completely drop this process and we just use one compressor which compresses isentropically all the way till this isobar. So you extend this isobar and you compress all the way till this point. You get rid of this impossible compressor. Okay, so now this leads to the first deviation from your reverse Carnot cycle. And the second deviation comes from the expansion side. Okay, so if you now remember your steady state, steady flow analysis of compressors and expansion devices. So if you apply the first law across any compressor on an expansion device, let's say 1 to 2, and this is the work transfer, you will get work transfer equals to m dot, what is the mass flow rate of the fluid across it, into H1 minus H2. Okay, and this, if you remember, turns out to be integral VdP. This change in enthalpy, VdP being the V being the specific volume of the fluid, and dP is the pressure difference across it, and you integrate it between the pressure at 1 to 2. This you remember, this expression? Or was it not taught to you? Okay, so this you have a look at from the thermodynamics text. So what is an important inference from this is, this is the expression for work transfer. Now for the time being, forget about the mass flow rate. Let's say it is 1. So if you are compressing a fluid which has very large specific volume, then the work transfer or work done by you would be very, very high. And hence, in order to compress a gas has very large specific volume, very low densities, and hence very large specific volume. So you have to do a lot of work. Whereas in order to pump a liquid across the same pressure ratio, you have to do significantly less work. So let's say you have to pump liquid from 1 bar, let's say, to 5 bar liquid water, and you have to compress steam from 1 bar to 5 bar. You will incur a huge amount of work in case of the steam compression compared to the pumping of liquid water from 1 to 5 bar. And the entire crux of that lies in this term V. If you have very large specific volumes, the work transfer is also very large. And hence you will see in all power cycles, the expansion process is always on the right hand side. Okay, by placing the expansion process on the right hand side, you are ensuring that you are expanding a fluid of low densities or high specific volumes, and hence you get large amount of work. Whereas you place all your compression or the pumping part on the left hand side in case of a power cycle, because you want to incur less pumping work or less compression work. So you give very little, but you gain a lot, and hence the net is what you gain from a power cycle. So we would want to place our expansion processes as far as possible on the right hand side to gain a lot of work based on this V. This is for power cycle. But now for a refrigeration cycle, the opposite is true. So if you keep this line as far as possible from this dome, you will have very large V's, but then you will incur a lot of work. So you want to actually place it as close to the dome as possible, but still keep the compressor safe. So if you push this to this point, you would have incurred less work. If you had it here, you would have a little bit more work. If you had it here, more work. And if you are here, you have even higher work. By just simply analyzing the density of the fluid which is undergoing the compression process. So if you place it somewhere here, the entire process, you will incur even more work. And hence, as I told you, the entry to the compressor should be at least saturated vapor. In fact, in order to minimize the work consumption, you would want it to be saturated vapor. So that is that limiting point where your compressor is safe, as well as your work of compression is also low. But if you push it to the superheated region, your work of compression increases because your specific volume keeps on increasing as you move into the superheated region. So this is all a game of balancing practical aspects and the aspects that come from the thermodynamics. Now, unfortunately, in case of a refrigeration cycle, your expansion process becomes the left-hand side one. So here, the density of the fluid is more towards the liquid side. So it would be significantly dense if you are expanding the refrigerant over here. Your V would be very, very less. Densities are high. So what you gain over here using a turbine would be a minuscule fraction of what you give to the compressor in the right hand side. Okay, theoretically, we should place an expansion device over there which is producing some work so that I can compensate, even if it be 10%, that 10% could be compensated over here. But in order to extract that 10%, I need to have another moving part in the system. I need to place it on the same shaft as the compressor because I don't want a generator placed inside my refrigerator. Okay, so I will keep the turbine or the expansion device as well as the compressor on the same shaft, and then it is connected to the motor because there is net work input in the cycle. So all these three have to be placed together, and now there could be another maintenance, another part which has to be maintained, okay, or another part which has to be provided with several years of warranty. So capital investment is high, maintenance could be high just to extract that 10% or 5% of additional work that we can get here. So we completely disregard this isentropic expansion process and we move to a lossy process. So this would have been a reversible adiabatic process. We remove this and we place just a simple valve over here which drops the pressure from P3 to P4. Dropping the pressure is not at all an issue. Okay. So we replace that reversible process with an irreversible process, hence the dotted line. And this process is the throttling process where the pressure is dropped from P3 to P4 by means of a valve or a capillary tube, which we will see in due course of time. So it is just reducing the pressure. Only issue now is, now I cannot reverse this cycle. I cannot go back to a power cycle with this configuration. This could be reversed, yes, this could be reversed, yes, this could be reversed, yes, this cannot be reversed. I will have to replace this throttling device back with the reverse of an expansion device, that is a pump or a compressor, to get back the power cycle. Okay, so what you get over here is the vapor compression refrigeration cycle. Okay, which in true sense you cannot reverse. Okay, so this is a cycle which you revert back and you will not get the power cycle. Now where we have taken the hit? Where we have taken the hit is, if you see, this would have been the process in case we had an isentropic expansion. My heat absorption would have been this. How can I simply say that this is the heat absorbed in the evaporator? Let's consider this as 4 prime. You had an isentropic expansion. This was the process. So how can I simply conclude that 4 prime to 1, the amount of heat absorbed in the evaporator is simply the area under this curve? How can I simply conclude that? Can anyone tell me? So what I am telling is H1 minus H4 prime is equals to the area under this rectangle. 1, 4 prime, let's call this A and B. Can anyone tell me how this is obvious? You know this expression TdS equals to dH. What is the other part? dH minus V dP. This you have come across? Or TdS equals to du plus PdV. This expression you have come across?
Yes, sir.
So if I apply the first law across this evaporator, the net heat transfer to this heat exchanger is nothing but the change in enthalpy of the fluid across the evaporator, that is the dH. And now in this case the process is isobaric. So dH equals to TdS. So from 4 prime to 1, or be it 4 to 1, whatever it is, wherever your integration limits are. So it is nothing but the area under the TS diagram. Okay, similarly, I can conclude that the heat transfer in the condenser which is nothing but H3 minus H2. That is also the area under the curve from 2 to 3, because it is also occurring on an isobar. So this would be the net heat transfer in the condenser. So just by looking at the area under the TS diagram, I can conclude about the change in enthalpy across the component. That's why we prefer TS diagram in most of the cycle plotting. Any doubts over here? Till now, any doubts, any queries? Okay.
Sir, why did we change the path from 3 to 4? I did not get that.
Okay. Okay. So let's consider this point as 4 prime. So this would have been a turbine over here. The device which would have extracted work in an isentropic manner would have been a turbine, isn't it? So this part you understand that the amount of work that you obtain in the 3 to 4 prime process is going to be a small fraction of the work which you are consuming from 1 to 2 process. This part you understood?
Yes.
Okay. So again, it is a practical call that we have taken, that in order to extract that 10% work from a turbine, first we have to place another rotating device in line with your compressor. You will incur more additional capital investment initially. You will have some maintenance of that additional turbine that you are operating. You can have failures for that also. Okay, so in order to reduce the cost and keep the maintenance of the entire system just limited to one rotating device, we have dropped this. There is no one stopping you from placing an additional device and getting some small amount of work and using it for improving the efficiency of the cycle. It is just that it becomes very cost ineffective for obtaining that 10% work. You will still have another, either a reciprocating expansion device or a turbine placed in your air conditioning cycle. Okay, so this is just a practical call that we have taken. Now consider a situation where you can have, let's say, 10,000 refrigeration ton capacity. Now over there, that 10% can lead to still, let's say, a few tens or hundreds of kilowatt. There it still makes sense because you are still obtaining some power of the order of 10 or 100 kilowatt by placing a turbine over there or an expansion device which is providing you some work output. But consider a domestic refrigerator which has 200 watts capacity, 300 watts capacity. By placing the best expansion device, you may obtain 5 watts of energy output, or maybe 10 watts or 20 watts of energy output. Now for obtaining that 20 watts, you are placing another device, a device which will be very similar to your compressor, which that will also require some maintenance, or it will also incur some capital investment. So it doesn't make sense in such small systems to place an expansion device which produces work. So that's why we replace it with a throttling device, because all we need to do is drop the pressure from this to this. Dropping pressure is not an issue. Did I answer your question?
But we can also shift the line towards right to
Towards
get
right,
more work.
to get more work. Okay, but
Though
then
we'll get
what will happen
less
is
heat.
less refrigeration capacity. So that's what I was trying to show you. Now from 4 prime to 4, by making this change, what we have done is we have lost some amount of refrigeration capacity. So that's why I was coming to the area under the curve part. So as you shift this to the right, you will start moving to a point where you will be generating lesser and lesser refrigeration capacity. Okay, so what your main target was to produce cooling. It was just that your cycle was also providing you some work output here, and you were utilizing that to offset some amount of work input. And what I am telling you is uh, from the practical scenario, it does not make sense, especially for small systems, even for medium scale systems, to have a work producing device in your AC or your refrigeration system. Only when it goes to extremely large capacities, do you see the cost benefit of putting a turbine of, let's say, which is generating 50 kilowatts or 100 kilowatts of energy, and driving a compressor which is probably consuming 1000 kilowatt. So there you may see a benefit, because that 100 kilowatt, that could be a cost effective system than having an expansion device for 10-20 watts of recovery. And when you want to recover more, as you said, I push this side to the right hand side, then I start losing on the refrigeration capacity. My aim was to produce refrigeration. Okay, so you can think of a Carnot cycle whose left side and right side are almost like this, very close to each other. You would be producing a lot of work here and consuming it in the compressor, and only small amount of input is needed, but then only a small amount of refrigeration capacity is also produced. So in order to keep the cycle simple, we just remove this turbine over here and replace it with the throttling valve. Is it clear?
Yes, sir.
Okay. So now coming back to the area under the curve part. So if I would have maintained the isentropic expansion, I would have obtained this much of additional refrigeration capacity, which I am foregoing, and I am foregoing some amount of work that I could have produced over here. Okay. And another thing that I am losing on is, in case of the Carnot cycle, so the baseline is again the Carnot one, I have some additional work input in form of this area. So this triangle has come. Earlier it was just this rectangle. So the net work input was the area of this rectangle. Okay, but now the net work input will be the area of this shape that is created. This is my refrigeration capacity, and this is the net work input, whatever I have marked with this red line. Now how do we get that? So COP of any refrigeration system is Q evaporator by W net, and what we are focusing is on this W net now. Q evaporator is the amount of heat which is transferred in the evaporator. Okay, that is where you are generating the cooling. So this is nothing but the area in this blue shaded region. That is quite easy to understand. Now how to get this work net in form of the area under the TS diagram. So what is the net work input to the compressor? That is H2 minus H1. Okay. So this part you just remember, H2 minus H1. So how to get that? Let me go to this part. Okay, so this is the H2 minus H1. The enthalpy at this point 2, enthalpy at this point 1. Okay. Now from your first law of thermodynamics, we can also write that the net work input is nothing but Q condenser minus Q evaporator. Can I write this? Okay. So if you are finding it difficult to understand, let's work with the H2 minus H1. H2 minus H3 minus H1 minus H3. These are simple modifications. Now, what is the throttling process? H3 equals to H4. This is the throttling process, and hence I can replace this now H2 minus H3, H1 minus this 3 with 4. Now this will make it quite obvious. Now H2 minus H3 minus H1 minus H4. H2 minus H3 is this area. H1 minus H4 is this area, the blue shaded area which I had called as Q evaporator. Whatever is remaining is your work input. Okay. This directly comes from the first law of thermodynamics. Del Q is to del W. There is some heat transfer here in the condenser side. There is some heat transfer here in the evaporator side. No heat transfer in the throttling valve. No heat transfer in the work consuming device. Okay. No work transfer in the throttling valve also. So only work transfer device is the compressor. So this cyclical integral del W just becomes the del W of compressor, and this cyclical integral del Q still remains, which is nothing but Q condenser minus Q evaporator. So nothing is violating the first law statement. The statement was for a thermodynamic cycle. The cyclic integral of del W and cyclic integral of del Q are equal. Okay, so it was probably not very obvious from the cycle itself, but once we look at the individual process, I hope it becomes quite obvious. So H2 minus H1 is the work consumed by the compressor. I just made some modifications. H2 minus H3 minus H1 minus H3. Replace this H3 with H4. So this is your Q evaporator. This is your Q condenser. Any doubts? Okay, good. So now if you see, if you compare the cycle that we have now discussed, VCRS cycle, and compare it with the Carnot cycle. So in the Carnot cycle, if I had written the COP, I would have written the refrigeration capacity as the area under this big rectangle. Okay, so let's call this AB. If I call it C, AC1 4 prime. So Q evaporator definition is still the same, work done by the compression. So in this case, it would be network. Okay, so the area under 4 prime AC1 divided by the area of this rectangle. In the case of Carnot, the area would have been 4 prime 1 2 prime 3. This is for Carnot. But when we shifted our cycle to this VCRS cycle, now the numerator has reduced by this much. So now we are getting less refrigeration capacity or less cooling effect, and the net work input has increased. Okay, now the net work input is this entire area. So we have taken a hit in the numerator, we have taken a hit in the denominator also. And hence the VCRS system will have significantly lower efficiency, or in this case it is called as the coefficient of performance, COP, than your Carnot cycle. But now you are at least sure that your compressor would be safe. You will not have those issues of very slow operating compressors, isothermal compression process. Nothing of that sort is there. Those are impractical devices. And we have also kept our initial investment as less as possible by removing one of the work producing device. Okay, so this is the practical change from your Carnot cycle, or reverse Carnot cycle, I must say. Okay. Any doubts or any queries till now? So sometimes we look at the efficiency of this VCRS cycle vis-a-vis your Carnot cycle. So you can take a ratio of it and you can actually evaluate how much or how far away from the Carnot COP you are operating at. Mind you, it is still an ideal cycle because we haven't considered any pressure drop in the heat exchangers. Okay, we haven't considered any superheating over here because we are assuming it to be saturated vapor. Later on, we will see that it is very, very difficult to maintain this exact condition. Okay, so now let's focus on these losses. Sorry, let's go back. So let's focus on these additional losses that we are incurring. This is one loss, this is one loss. The top triangle, this loss we have taken by removing that isothermal compression process which was happening over here. We have removed that isothermal compressor and we have placed one single compressor which does the entire compression from 1 to 2. And we incurred one additional area under this curve. So this is called the superheat horn. Superheat horn. Just a name given because by the time the gas comes out of the compressor, it is significantly superheated. Okay, it is no more at the saturated vapor point, it is superheated. So hence this additional superheat that we are incurring, this horn signifies that particular loss when compared to your Carnot cycle. And this rectangle that we are seeing over here is called the throttling loss. So this loss we have incurred by replacing a turbine with a throttling device. So hence this is called as the throttling loss. Now this throttling loss and the superheat horn, these losses itself can change based on the property of the fluid which we are using as the refrigerant. So if you change the working fluid, in this case it is the refrigerant, you will see that this area and this area continuously changes. So you try it out with R134A, you try it out with R12, R22 for similar operating conditions. You will see that these areas will be different for each. So either if you change the operating condition, these areas will change, or if you change the refrigerant itself, these areas will change. Okay, so let's take a quick tour on how even the material scientist started thinking in the lines of minimizing these losses. So how we came up with synthetic refrigerants? There must be some directionality for that. Why we have devised only these particular refrigerants which we are using? So there was some idea. The idea was to minimize these losses. Okay, by suitably modifying the properties of the fluid which we are using. So of course, people have analyzed all the natural refrigerants which were available, like water, okay, CO2. Okay, so whatever natural refrigerants which were available, so people have analyzed and saw that these losses are a particular percentage of the area under this rectangle. Now, how to reduce these areas? So let's slightly change our analysis of the throttling loss. Throttling loss was this. So we have realized that this rectangle is the throttling loss. So let's change our analysis such that the throttling loss, which is area under this rectangle, comes out to be area under something else, and that will have direct correlation with the properties of the substance. The property of this pure substance which we are looking at is the liquid plus vapor dome, this dome itself. So this dome is not fixed for all the refrigerants, so it can change its shape. Okay, so we will derive this area in some other way, and it will lead to some other area under the curve, which has more direct correlation with the shape of this dome. So just like what I had done is H1 this H2 minus H1, I replace this H2 minus H1 with H2 minus H3, and this H1 as H1 minus H3, and then H3 and H4 were equal across the throttling device, and then we were able to derive that area under the curve. Now instead of writing H2 minus H3, what we will write it as is H2 minus HF prime. Now what is this HF prime is, if you extend this isotherm and if you extend this isobar, wherever they intersect, that is that point F prime. Okay, and you do the same thing for H1 minus HF prime. Okay, this I have already told you. So H2 minus HF prime would be the area under this curve. And now comes a big dose of approximation, HF prime and HF. Now what is this F? F is the point on the saturated liquid line. So if I extend this isotherm, wherever it hits the this saturated liquid line, that point is F. Now the approximation is HF and HF prime are almost same. Now how can I make this approximation? Let me go one slide ahead. This is the actual TS diagram of R22. Now you see this is the pressure line. These are isobars. Okay, so you can see 0.2 megapascal all the way till 100 megapascal. Okay, so this is this black line, black line. Now all these isobars are so closely packed in this region. Okay, so if I intersect one particular isobar at somewhere this point, and instead of making that F prime, I approximate that F prime with F, I will not be making a huge error in terms of the x-axis. Okay, so all these isobars are bunched up together, and this is because of the incompressibility of the fluids in the liquid region. In the liquid region, all the pressure lines are very, very close to each other, whereas they are far apart in case of the vapor side. And hence on the left hand side, I can make this approximation. Not convincing enough? the point F prime and F will be very close to each other. Can you see it from this plot itself? Yes or no?
Yes, sir.
Okay. So only one yes. So I'll assume that others also agree. Okay. So let's see what is the advantage by doing all this manipulation. So what I will do is now replace F prime with F, and now I will have H2 minus HF prime as H2 minus HF. So that will lead to this area. Okay, and H1 minus HF is this area, this particular area. Now, if you subtract those two, what you end up with is this as the net work done. So what we have done is, now in the previous slide we had concluded that the net work done was this area. Let me change the color. So in the previous slide we have concluded this was the net work done area, and now we are concluding that it is almost equal to the other shape which we have derived in this slide. It means that this throttling loss is similar to the area of this particular triangle. Now this particular triangle area will change based on the slope of this line itself. So that has a direct connection with the property of the substance. So now if you have a particular fluid built in your chemistry lab and you somehow get all the property values at different pressure, temperature, and you plot it and you get the dome, based on the shape of the dome, now you can make some estimation of what would be the area. This is equal to now the throttling loss. So this area is also now equal to the throttling loss. Okay. So what we have done later on is we have started classifying the refrigerants. So since we are building we are synthesizing refrigerants in labs, so we have now some idea of what is desirable, what kind of properties are desirable, what is not desirable. Okay, so ideally would be the smallest A4 and the smallest A3. So we don't want this throttling loss to be very high. We don't want this superheat horn to be very high. That would be the ideal refrigerant which is available to us. Okay, but once we started synthesizing these refrigerants and we checked the properties, so we were able to classify majority of them into two types. So type 1, where most of the natural refrigerants lie, is where your superheat horn, this triangle and this triangle, are equally significant. The ones that we were able to synthesize in labs, they fall under the second category. You see all the synthetic refrigerants are there. So not all, but majority. They were refrigerants which have smaller amount of area under this superheat horn. But we were not able to reduce the throttling loss area. So this we still haven't been able to reduce, but we were able to reduce the superheat horn. So the shape of this dome is such that this area under this triangle was smaller. And in our quest of newer and newer refrigerants, we were then able to synthesize another category, type 3, okay, which is not very commonly used. it would be evident from the property. This dome itself is having a shape like this. It is no more a symmetric parabola kind of a thing or slightly offset on the right hand side. This one is so offset on the right hand side that this line slope is completely different from the type 2 or type 1. So this has a completely opposite slope. Now the issue with this kind of fluid is, even if you have saturated vapor condition at the inlet to the compressor, you end up in the two-phase region after compression. Okay, so not a very good type. So you will see we normally use type 1 and type 2. So type 2 is the one which is prevalent in all the refrigerators and air conditioning systems. Okay, type 3, of course, we synthesized in lab, we were able to classify that, but very limited practical use, because you will have to give some superheat at the suction of the compressor. So you have to ensure that the suction to the compressor is having that much superheat, so that even after compression, isentropic compression, we do not end up in the two-phase region. Okay, so it will have very small amount of superheat on. So we were not able to reduce the throttling loss, but we were able to reduce the superheat horn. We were able to reduce here, and we were able to reduce it so much that the point 2 went inside the dome. Okay, so this is how we have progressed in our synthesis of the refrigerant. So that was the quest. Any doubts?
Sir,
Yeah.
in the slant line from the point 2, which parameter is constant there?
Which one?
The triangle slant.
This one? This one? Left one? This left one?
No, the right triangle.
Okay, the right, this one. This slant line.
Yes.
Isobar. This is isobar.
Okay.
Okay, so that's why it is very, very important to know the properties of the working fluid which you are working with. That determines a lot of parameters. So even from thermodynamics point of view, you can fix which refrigerant to be used. Now we are in an era where we are restricted by the environmental policies, and hence that is given the primary choice, and we are shifting to refrigerants which may not be so efficient from the thermodynamics point of view, but they are safe from the environment point. So that is an additional constraint. But think of the 1900s, 1950s, 60s, people didn't care about the environment. All we cared about is कितना कम बिजली लेती है ये. That's it. So that was the quest, and that is how. So this is the feedback which engineers would have given to the chemist, and the chemists in the lab are producing refrigerants, classifying them. Okay, they are measuring the properties, coming back, and they would have developed some correlation between the molecules that they are adding, or the chain, the alkane chain or the alkenes, and their physical properties or thermodynamic properties. So some kind of a calibration would have been done, and that's how people would have thought, okay, let's move to the next refrigerant, which will have this chain, and that will lead to this kind of a property, and we'll be able to reduce the losses. So as a homework, actually, what you can do is consider ammonia as one of the refrigerant, and consider R134A as the second refrigerant, and check the T2. Okay, you need not carry out the entire analysis of the cycle. Assume that the evaporator temperature is 10 degree. Will not change the operating condition. Okay, condensing temperature is 50 degree. Condensing temperature is this horizontal line and not T2. So you have to find out the saturation pressure at 50 degree and then that fixes this isobar. Similarly, you will have to find out the saturation pressure of R134A and that will fix the isobar. So condensing temperature is the temperature in the liquid plus vapor region. But the gas which comes out of the compressor is significantly higher than the condensing temperature because it would be in the superheated region. So do not assume that I am telling condensing temperature as 50, it doesn't mean the discharge temperature is 50. So as an homework, what you do is fix the evaporator temperature as 10 degree, fix the condensing temperature as 50 for both ammonia and R134A, check the T2 for ammonia, check the T2 for R134A. Just check this temperature. So that is another thing that you would be able to conclude for type 1 and type 2 refrigerants, which I have not mentioned here. So just make a conclusion on the discharge temperatures. Okay, so this is your homework. So next week I will ask what you have observed. So just check the compression process and tell me what is the discharge temperature for ammonia, what is the discharge temperature for R134. Okay, so that is another difference between type 1 and type 2, which I have not mentioned in this slide. So now the refrigeration industry is not obsessed with the TS diagram. The refrigeration industry is very much obsessed with the pH chart. Now, why pH chart? So this is the pH chart of a typical working fluid. Okay, do not confuse this dome shape with the shape for the type 3. Okay, this shape is obtained on a TS diagram. Okay, this is obtained on a pH chart. So even this type 2 will change to this shape. So what is the advantage of shifting to the pH diagram? So why refrigeration industry always uses pH chart is we can replace the throttling line which was at a particular slope on the TS diagram where we cannot determine exactly where this 0.4 will lie. Now on a pH chart, since the throttling process is an isenthalpic process, 3 to 4, it becomes a vertical line here. Okay, so this left hand side becomes a vertical line. Of course, it should be still denoted by dotted line because it's an irreversible process. But in this chart, it is not done so because there are dotted lines for isotherms. So this should still be dotted line and the rest of the three processes are solid line just to denote that they can still be reversed. Okay, so the isentropic line now, instead of becoming a vertical line, that comes now at a particular slope. Okay, now the isotherms are like this, as shown by the dotted line. Isobars become now horizontal lines. Since we are working with two isobars, one isenthalpic line, so now this becomes an easier way to represent, except for the isentropic line. Rest all the three lines are now either horizontal or vertical. So that's why refrigeration industry, they like to use this chart instead of the TS diagram. Now, can you tell me why these isotherm lines are vertical, almost vertical in the liquid region? So these questions I continue to ask so that I can test and help you correlate these property lines with the equations that you would have studied in your thermodynamics. Otherwise, we just solve problems in thermodynamics. We do not go in depth and understand what is happening. So why these isothermal lines? They look like a vertical line in the liquid region on this pH diagram. Can anyone give a reason? This is not a printing error, huh? So this is how it is actually. In the liquid region, what is the expression for dH? Change in enthalpy. Let's say in the subcooled region, subcooled water, I want to know, or I want to write an expression for change in enthalpy of water, subcooled region. What equation do I write? What equation do I write? Cp dt, isn't it? Per unit mass. Now, if you have an isothermal line, what it turns out is it also leads to an isenthalpic line. This is only valid for the subcooled region. Or is it valid for some other region also? Where else can I write dH equals to Cp dt? Anybody? Where else can I write dH equals to Cp dt? Can I write it in the two-phase region? Liquid plus vapor region. Can I write it here? dH equals to Cp dt. Guys, I need some interaction. Otherwise, it is just a monologue. Or do you want me to call names? So where else we can write dH equals to Cp dt? Can I write it in the two-phase region? Liquid plus vapor mixture?
No, sir.
No. Where else? So in the subcooled region, I can write, and hence an isothermal line is also an isenthalpic line, and hence they look like vertical. But where else I can write dH equals to Cp dt? The ideal gas region. So ideal gas region is far away from the dome, somewhere here. This would be an ideal gas region. Okay, and that's why you start seeing that this isotherm again starts to turn into a vertical line as we move further away from the dome. So as I move further and further away from the dome, my ideal gas assumptions start becoming more and more valid. And hence these lines again turn back into a vertical line. So you must question when you see these property lines. What is happening? Why this is happening? So over here and over here, the expressions that you have learned in your school, in your second year thermodynamics, they need to be valid. And hence the property lines also show the validity of those expressions. So the same R22 now on a pH chart looks like this. Okay, so the book from which this is taken, the publisher of that book, he didn't even bother to put the isotherm lines in the subcooled region. You do not see those lines, isotherm lines. They just mark -10, 0, 10, 20. So these vertical lines, the isenthalpic lines, are more or less the isotherms over here. Okay, whereas you see these isothermal lines coming out from the saturated vapor region, these red colored lines, and they are going over here in the superheated region. And as they move away, you see, if you move further away from the dome, again these isothermal lines, they look like almost like isenthalpic lines. Only near this region and the supercritical region you see them curving. Okay, so this is all about the pH diagram. Any questions till now? Okay. So let's come to the next subtopic, that is a small modification is done to the VCRS system. Okay, that modified cycle is also a part of one of the lab experiments that we will do. So let's revisit the cycle. So since we are familiar with TS diagram a lot, so let me still continue with the TS diagram. 1, 2, 3, 4. Now let us understand what limits the temperature at point 3. See, if I am able to expand or throttle the liquid from point 3 to 4, this is the refrigeration capacity that I generate. Okay. Rather, I should say the refrigeration effect, because we are not looking at the mass flow rate. Well, this is nothing but the cooling effect. Now, suppose I, instead of expanding from point 3, I am able to expand from this point. Let's call this as 3 dash. Then I would be able to gain some additional cooling effect. Furthermore, so if I am able to subcool this, I would be gaining even more. So what limits the temperature at point 3? So the point 3, or in this case 3 prime. So what limits the temperature after the condenser? Can anyone tell me? This is from practical scenario. So where is the condenser placed? It is placed outdoors. So what limits the temperature at point 3 or 3 prime? So at the exit of the condenser.
Ambient temperature.
Ambient temperature. Good. So even though theoretically we would want the temperature at the exit of the condenser to be as low as possible, so that we can gain as much as possible in the evaporator, but there is a limit, and that limit is not in our control. So today, now the Kharagpur outdoor weather would be around 20 to 25. So I would be able to theoretically lower down the temperature to 25. But again, a heat exchanger has to operate across some delta T. So maybe at 30 or 29, I would start seeing diminishing returns. I will not be able to go below that. So 3 to 4 degree C temperature difference will remain when compared to the ambient. Now, when the same AC is being is used using the summer, peak summer, it would be around 45. So if the ambient is at 40, my condensing temperature could be around 45. I will not be able to go below that. So is there a way to artificially cool this? Is there a way to artificially cool this liquid? So this is already saturated liquid. I want to further reduce the temperature. Is there a way by which I can achieve this? Just look at the temperature at 0.3 and look if you have within the cycle somewhere a temperature which is significantly lower than T3. Where is that? There are only 3 more points remaining, 4, 1 and 2. 2 is definitely not going to work. 2 is definitely higher than T3. 4 and 1. So this temperature. Now after the evaporator, as it goes to the compressor, this refrigerant is at a temperature of T1, which is equal to T4. Now what if I subcool the refrigerant which is coming from the condenser using this refrigerant itself? So there is an internal heat transfer between the condenser outlet and the evaporator outlet. So this is the condenser outlet, some kind of a heat exchange between this and the evaporator outlet, which is this. So what will happen? I would be able to subcool the refrigerant, but it will not be free. That will lead to some amount of, what will happen to 0.1 then? What will happen to 0.1 by the time it exchanges heat and then enters into the compressor? Where will it shift from saturated vapor to
Superheated.
superheated? So this point will shift somewhere to this, and 0.3 will shift somewhere to here. So I will gain on the amount of cooling I am producing, but there is a penalty. What is that penalty? What is the problem in terms of thermodynamics when you have superheated entry into the compressor? You have shifted your compression line now towards the right hand side. So you will incur a penalty in terms of work of compression. So superheated vapor will have a higher volume, specific volume when compared to saturated vapor, and hence my VDP work will increase because I'm pushing the line now from this blue line to the red line. I will also take a hit in the discharge temperature. Earlier the discharge temperature was this, and I will have slightly higher discharge temperature, which means that my compressor will also run a little bit hotter, because discharge temperature is the temperature after compression. So if I look at the overall COP, so that is Q evaporator by work of compression, it is difficult to conclude if I would be able to improve the COP. So Q evaporator goes high, but work of compression also goes higher. So there could be one optimum value at which this COP can peak, or there is a possibility that COP may not peak at all. It can continuously decrease. So this heat exchanger is called the we will just straight away go to the this heat exchanger is called the liquid to suction heat exchanger. So now this is the modification that we are looking at. After the evaporator exit, we have a heat exchanger which cools the condensed liquid coming from the condenser outlet. And then this vapor enters the compressor. This liquid after subcooling enters the throttling device. So this name is given liquid to suction heat exchanger because this is a heat exchanger between the liquid line and the suction line of the compressor. Liquid line and the suction line. Okay, so the analysis part, the first law analysis part is quite simple. Just apply the first law and then you will be able to obtain that the enthalpy drop across the liquid line would be equal to the enthalpy gain by the vapor line. Okay, and we are able to do so by just internal heat recovery. That's it. Okay, but remember that this may or may not lead to an increase in COP, but this will definitely lead to an increase in the refrigeration effect. Okay, so with the same amount of mass flow rate of refrigerant, you will gain some amount of cooling effect. Now, there is another reason why we make use of this heat exchanger is just think of how the AC's indoor and the outdoor unit is mounted. So let's say this is your indoor, and let's say at some height, your outdoor unit is mounted. You have the refrigerant pipes going in and coming out. Okay, so one line. So this is indoor unit is nothing but your evaporator. Outdoor unit has the compressor and the condenser. So this line which comes out of the evaporator, that is the indoor unit, and goes to the compressor. So this is the suction line. And the other line which comes in to your evaporator also has so your indoor unit also has the throttling device placed here, somewhere here. So your indoor unit has the evaporator and the throttling device. So this line which comes here is the liquid line. And then you would see that the AC mechanic puts in an insulation, a black colored insulator on that, and then he puts an insulation tape on that, and then pushes the pipe out through a hole here in the wall. So this is to prevent the outdoor heat heating the suction line. The liquid line is already close to the ambient temperature, so there is not significant heat transfer between the ambient and liquid line. But the suction line is already very cold because it is at a temperature close to the indoor temperature. So there the insulation is very, very important. So what these AC mechanics do is, knowingly or unknowingly, what they do is they will place this liquid line and the suction line together, and then they will take it out. Okay, together into one single insulation, and then they will take it out. So what they are doing is effectively transferring heat from the suction to the liquid line. Because if they would have taken two separate pipes with separate insulation, then there wouldn't be any heat transfer. Then there is a chance of the suction line having a lot of heat transfer with the ambient itself. None of the insulators are perfect, and when they are externally kept with the continuous weather variation, you can see those insulations also start getting destroyed. And somewhere, maybe after a few years of operation, you will see those insulations break down and the tubes become exposed to the ambient, which is not a desirable thing, because the suction line will then gain heat from the outside, get superheated, and then enter the compressor. So it is better then to just exchange the heat between the suction line and the liquid line, and they will place them together, and then they will place one single insulation tape over it. Okay, so they are unknowingly placing this heat exchanger. Now, if you do not place this heat exchanger, this line which goes to the compressor, especially in the case of split ACs I am talking about, window ACs do not have this issue because there everything is mounted in a single unit. Okay, so when you are placing the outdoor unit outside, especially very far away from the indoor unit, you can gain heat from the outdoor. So that gaining heat will also lead to some superheating before the vapor enters the compressor line. So that superheat is of no use. So that superheat is called useless superheat. So you're not gaining any cooling effect. It is just the heat from the ambient has penetrated into the suction line. If your insulation is not proper, or after a few years of operation, the insulation breaks down, you have exposed pipes on the outdoor. So then whatever superheat is gained by the refrigerant by the time it enters the compressor, that is useless superheat. Okay. Sometimes the manufacturer also design the evaporator to have small amount of superheat by the time it leaves the evaporator. So that is not useless superheat, that is useful superheat. So you will get some amount of additional refrigeration effect within the indoor unit itself. Now this is to ensure that the gas is always in the vapor region by the time it reaches the compressor. If a designer designs the evaporator to operate exactly at saturated vapor condition for a particular design condition, if the operating condition changes, there is a chance that your evaporator becomes undersized for the other operating condition, and you have liquid also going into the compressor. So just to ensure that, many a times the evaporator is oversized, and that oversized evaporator leads to some amount of superheating in the indoor unit itself. So that is useful superheat. But if it gains superheat from the outdoor insulation not being properly installed, then that is useless superheat. And what we do in order to ensure that the heat is not transferred from the ambient is we place the suction and the liquid line together, and then we put the insulation. So those two pipes are in contact, thermal contact. So there can be some small amount of superheating of the suction side and subcooling in the liquid line. So we need not have a separate heat exchanger per se. Okay, so we'll continue from here. In case anyone has doubt, I can take the doubts now.
Sir, but here still the work required is more.
Yes, work required is more. Yes, work required is more, but we are getting some amount of useful refrigeration effect out of it also. Yes.
So, but we did not make sure that the COP is increasing or decreasing.
We did not. Yes, but especially in case of the split ACs, when we take the suction line out, anyhow there is some amount of superheating going over there from the ambient. Okay, so better to get the liquid line in direct contact with the suction line than your ambient giving the heat to the suction line. But you can find out from thermodynamics point of view that what is the optimum superheating, or if at all there is any optimum superheating for a given refrigerant for a given set of operating condition. That can be obtained from thermodynamics by a cycle analysis. But it is very, very difficult to operate in that region, especially when we have the outdoor unit kept completely outside with the pipes going out, where they can gain some useless superheat. say for your refrigerator, where everything is inside in a very well-defined environment, that is your indoor house. So there you can provide a heat exchanger which operates very close to the optimum superheat, if at all it exists, for your operating conditions, because the operating conditions do not deviate significantly in case of a refrigerator, but it significantly changes in case of an AC.